Thank you all for joining this particular webinar. I thank you, Professor Arun Pratap, for inviting me at this particular place. The topic that I'm going to talk about is basically fundamental topic in quantum mechanics. It is the uncertainty principle. Let us begin the topic straight away. So, as far as the science is concerned, this is just there are many important events that occurred in science. I have listed them in order, not in any order, but just the way that they came to my mind. One of them is Origin of Species by Darwin. Then another important process is synthesis of urea in laboratory by Wohler, which basically made that organic chemistry can be studied in laboratory. Understanding of genetic code by Crick and Watson. Invention of number system and role of zero in real and complex plane. Fleming's discovery of penicillin. Another important theorem is Gödel's impossibility theorem, which is very important in our studies also, because yesterday somebody was talking about that can quantum mechanics tell everything about science. Well, Gödel says that whatever, because every science has certain assumptions, and Gödel has shown that it is impossible to derive everything or prove everything using these assumptions. So therefore, quantum mechanics cannot answer all the questions, because nobody can answer all the questions. In our Upanishads, there is a statement which basically says, Sahasraksha Sahasrapat Sabhumim Vishwato Vrutvat Atyatishtat Dashangulam. He says that the God has thousands and thousands of eyes, thousands and thousands of hands, and so on, and it envelops the entire universe, but it stays 10 angles, 10 things about that particular thing. That means even God cannot be explained by using our assumptions. Anyway, that is another thing. As far as the physics is concerned, Newton's theory of gravitation, Oersted's experiment, Maxwell's equations, Einstein's theory of relativity, thermodynamics, quantum mechanics, nuclear energy, these are the basically the signposts in physics. Let us go to, and then the list is actually very long. Each of these basically has changed our thinking and has revolutionized the science. As far as the topics are concerned, everything in this world is connected to one another. All right. We actually compartmentalize because we call ourselves physicists, some chemists call chemists, and so on and so forth. There are different departments and so on. There are rivalries in the department. But as far as that is concerned, we compartmentalize simply because our time is limited, our brain size is limited. In principle, this compartmentalization is basically because of our inability to understand everything. There is a poem by John Donne which basically says, no man is an island entire of itself. Every man is a piece of the continent, a part of the main. Any man's death diminishes me because I am involved in mankind, and therefore never sent to know for whom the bell tolls. This is basically a mythological poem which basically for whom the bell tolls. The bell normally tolls in the Christian where a certain person has died and the John Donne is buried. I do not believe that there ever was such a time. On the other hand, I think, and I can safely say, nobody understands quantum mechanics. Nobody knows how it can be like that. This is a quotation from Character of Physical Law, which is written by Professor Feynman. Similar feelings Professor Einstein also mentioned. This also was mentioned yesterday, that all 50 years of my conscious brooding brought me no nearer to the answer the question, what are light quanta? Nowadays, every Tom, Dick and Harry thinks he knows it, but he is mistaken. That is basically what Professor Einstein wrote a letter to his friend. The main concept which gives the uncertainty principle, Heisenberg's uncertainty principle, is basically the question of duality. The duality is basically wave-particle duality. Light, as we know, shows interference effects, Young's double-slit experiment, then photoelectric effect, and matter has electrons, protons, and neutrons. So light as an interference basically shows a wave character. Photoelectric effect shows the particle characteristic, while matter, electrons, protons, and neutrons, particles, these are particles, as Professor J.J. Thomson proved in earlier of the last century, and his son, basically another Thomson, showed that it is a wave. So therefore, description of a particle and description of light as a particle as well as wave, that basically corresponds to duality. This basically is a concept in our philosophy also. Our philosophy also talks about duality, Dvaita and Advaita. Anyway, let us not go into philosophy right now. Let us look at the uncertainty principle, which basically says that if it's a description as a wave, if matter is described as a wave, if light is described as a wave, then the wave basically is an infinite extent. It goes from minus infinity to plus infinity as far as one dimension is concerned. So therefore, in that particular case, its uncertainty in position is infinity, because it is present everywhere. As far as that part is concerned, the momentum uncertainty automatically is zero, because then the momentum is basically certain. If we describe that as a particle, then particle is at a particular place. And as far as if the particle is at a particular place, its uncertainty in position is zero. But whenever that particular wave function is described as a Fourier transform, it corresponds to have a waves which are superposed with waves from minus k is equal to minus infinity to plus infinity. So which basically means the momentum uncertainty is infinite. So therefore, as far as the product part is concerned, actually all particles, whenever we talk about electrons and protons in anywhere, that particular thing, electron is not really at from minus infinity to plus infinity. It is localized. So therefore, it has to form a localized wave packet. So localized wave packet, whenever it's described quantum mechanically, corresponds to a superposition of many waves, and AK corresponds to the amplitude of that particular wave. There is a very important theorem in Fourier transform mathematics, which basically says, it's written by Bracewell, and it says delta x into delta k is always greater than or equal to half. Now this is a theorem in Fourier transform mathematics, and that particular theorem basically says that whenever a particle is described as a wave packet or a system is described as a wave packet, then in that particular case, delta x into delta px would always be greater than equal to h bar by 2. So delta x, of course, uncertainty in position is defined as the square root of average value of x square minus the average value of x whole square. Similarly, corresponding uncertainty in momentum is defined. Now, in this particular case, whenever we talk about uncertainty, the probability enters the physics. Probability enters the physics in two different ways. One different way, it occurs in statistical mechanics. It occurs in statistical mechanics because there are so many number of particles that are there, and therefore it is our inability to know the position and velocities of all the particles, and therefore we are unable to actually unable to do the calculation, and therefore that basically corresponds to this is due to our inability to do the calculation and keep the track of all the particles. The second kind of probability enters quantum mechanics, as the quantum mechanics wave function is written down as psi, or the probability of a finding a system at a particular place is psi star psi. That is the interpretation given by Born, and that quantum mechanics basically is that is due to its intrinsic character. Anyway, the quantum mechanics also we have entrance of non-locality. All laws of physics earlier are considered to be local. That force on a particle is local and acceleration of a particle is local. So all these things are local. Whenever the quantum mechanics comes in, it automatically brings in the non-locality. That means the effect can be seen at somewhere else. We will come to that later whenever we talk about uncertainty principle. Now, as far as the uncertainty principle derivation is concerned, I am not going to talk about the derivation of uncertainty principle because it is given in many textbooks. So let us go ahead. And what I will here before discussing anything, I would like to show you a quotation from Professor Feynman, whatever he wrote in his lectures in physics. He says the uncertainty principle protects quantum mechanics. Uncertainty principle protects quantum mechanics. Heisenberg recognized that if it were possible to measure momentum and the position simultaneously with a greater accuracy, the quantum mechanics would collapse. So he proposed that it must be impossible. Then people sat down and tried to figure out ways of doing it, and nobody could figure out a way to measure the position and momentum of anything, a screen, an electron, a billiard ball, anything with any greater accuracy. Quantum mechanics maintains its perilous but still correct existence. The reason why Professor Einstein always attacked uncertainty principle is because uncertainty principle is protecting quantum mechanics. And Professor Einstein wanted that the God does not play dice. He does not want probability in the world. And therefore, that particular, he was always attacking uncertainty principle. Anyway, what I am going to talk about are various topics that are there, which basically are given here as a list. And I don't know how far we can go as far as that particular list is concerned, but let us go ahead. So first of all, it is the gamma ray microscope, which basically brings us how the uncertainty principle comes into physics. Because wavelength of light, whenever we observe anything, or let us say look at the microscope observes any small quantity, small object, then in that case we are using light as the source of information, so whenever the light is used, the limit of resolution is of course lambda by 2. So delta x, now of course that basically means the whatever is the objective of the microscope, that half angle of the objective is theta, and delta x, uncertainty in position, maximum uncertainty in position corresponds to lambda upon 2 sine theta, where theta is the half angle of the aperture of the microscope. So electron is certainly smaller than the visible photon, so we must use very small wavelength. So the small wavelength based so instead of using ordinary light, we use now gamma ray photon. Now the gamma ray photon has a momentum corresponding to p. Now if X-ray photon, gamma ray photon or X-ray photon enters the microscope in this direction or in that direction, then it has different theta that it enters. So therefore, X-ray X component of the photon, after scattering in anywhere in that particular in the lens of the microscope, uncertainty corresponds to p sine theta. So the X component of the momentum corresponds to p sine theta. So the momentum of course is conserved. So delta x, delta px corresponds to greater than h by 2. So this is how the basically whenever we want to observe anything, we cannot observe the quantity. If there is uncertainty in momentum, there is corresponding uncertainty in the position and corresponding uncertainty in the momentum. Similarly, diffraction experiment was yesterday talked about, and that also shows that there is uncertainty in the position as well as uncertainty in the momentum. Let us go ahead. One of the important milestone is an experiment that proposed by Einstein. There is a story that always goes on, and in fact it is written down many places, that whenever the Solvay conferences were there in Europe, Einstein would be present, Bohr would be present. The story goes that in the morning, Einstein would talk about how the uncertainty principle can be violated, or it is not valid in a certain region, and then he would talk to this to Bohr, Heisenberg and others that are there. Heisenberg and others would never listen to that particular part, but Bohr seriously took that particular thing. And by the evening, the dinner time, Bohr would have given the answer to the Einstein that your proposed experiment is not violating uncertainty principle, but in fact it is showing that uncertainty principle is valid. This is a famous experiment that Einstein proposed, that let us have a box which contains certain number of photons, and there is a shutter to that particular box that is controlled by a clock. So whenever that particular thing is then in that particular case, the mass of that particular entire box can be measured very accurately, and energy and mass are related to each other. So therefore, whenever the clockwork opens the shutter is open, the photon goes away in particular direction. So the mass of that particular box is reduced. So the mass can be measured leisurely, and the photon goes away. So the energy of the photon, so therefore the mass can be measured very accurately, and the energy also energy can be measured very accurately, and the time also can be measured very accurately. So therefore Einstein proposed to Bohr that this particular experiment shows that delta E delta T is not valid. Now there is a argument that Bohr gave. Bohr at that particular time used, in the evening, told Einstein that, Professor Einstein, you forgot your own theory. You forgot your own theory of general theory of relativity, because general theory of relativity says that whenever the gravitational potential changes, there is a change of rate of clock, and if that particular thing is taken into account, then you will immediately realize that delta T delta E is always greater than h bar. Anyway, that is the main important experiment, or the crux of quantum mechanics is in double slit experiment. Double slit experiment basically is, here is this is a figure from Feynman's lectures in physics. This says electron gun has two slits, and then there is a detector. If one slit is open, you obtain, this was also discussed yesterday by Professor Lokanathan and Professor Ghatak, and then one obtains, whenever both slits are open, we obtain an interference pattern. So therefore, Tonomura, who is also mentioned yesterday, that instead of having many number of electrons flowing, if the number of electrons in the entire experimental system is always one at one particular time, then also one obtains this kind of interference patterns. So somebody asked that particular time, does an electron interferes with itself? Well, Dirac actually says that each photon or an electron interferes with itself, because a electron that comes at this particular time and electron that comes later time are not coherent. But each electron, when it passes through both the slits, now it passes through both the slits is a question. How does it pass through both the slits? Well, there is a probability of passing through this slit, and there is a probability of passing through this particular slit. And if that is taken into account, then in that particular case, we obtain an interference pattern. So the interference pattern is an example of electron behaving like a wave. And of course, the question is, whenever electron is detected, it is detected as a particle. But whenever it moves from one place to another place, it moves like a wave. So therefore, both things are together. Yesterday, people were asking whether electron is a wave or electron is a particle. And then Professor Feynman used to say that neither electron is not a particle, electron is not a wave. In fact, he gave a name to that particular thing. It's a wavicle. Wavicle basically means it's a combination of wave and particle. Now that particular experiment, electron experiment, has now can be conducted, and this is an example where the carbon 60 buckyball, all right, such a large system also shows interference pattern. Now this is an experiment that has actually been conducted, and this is the same kind of an experiment with buckyball with lower resolution, but this is a resolution that is, this is an interference pattern on molecular interference, which basically says phthalocyanin. It's a complex uh, organic molecule, and such a large molecule also it's showing interference pattern. So the interference pattern is not only shown by photons, electrons, it's actually shown by many large molecules also. All right, anyway, let me go ahead and actually look at the applications of quantum uncertainty principle. Now it is a funny question, funny way to say that applications of uncertainty principle, because uncertainty principle is not an equality, it is an inequality. So whenever it is an inequality, we cannot actually derive things exactly, but we can understand many things using that uncertainty principle. And that these are basically what are the that gives us physical understanding of many phenomena in nature. First of all, it was used to show that electrons cannot remain inside the nucleus, because whenever the matter was studied, the first of all the protons were known and electrons were known. Electrons were the first thing that were discovered, and protons are the part. So the nucleus, when Rutherford discovered that particular size of the nucleus, then in that particular case the initial model was that the nucleus is made up of protons and electrons, because helium-4 basically has 4 protons and 2 electrons inside. That was the idea that was used earlier whenever the neutron was not discovered. But anyway, electrons, then later on one really found that electrons cannot remain inside the nucleus. Electrons do come out of a nucleus because of beta decay, but these beta decay electrons are not there, already there inside that particular nucleus. They are actually generated at that particular time. And this can be shown because the radius of the nucleus is of the order of 10 to the power minus 13 centimeter. So therefore, delta P, it corresponds to roughly h upon r0, and which corresponds to a value which has a relativistic formula has to be used, and that basically gives the value of about 200 MeV. So if electron is inside the nucleus, it must have kinetic energy of the order of 200 MeV. Now, the question may occur, delta P is of that particular order, why the momentum should be of that order? Now, if you look at the equation of delta P basically says expectation value of P square minus the square of the expectation value of P square root. Now, expectation value of P is 0 because the electrons inside the nucleus. So the expectation value P must be 0. So the expectation value of P square, which corresponds to uncertainty, and that basically corresponds to 200 MeV. Now, if the electron comes out of the nucleus, it must have kinetic energy of that particular order, of the order of 200 MeV. But as far as the beta decay is concerned, beta decays, the electrons coming out of the nucleus do not have energy much larger than few MeVs. Even if I consider that the electrons are attracted by the positive nucleus, and that particular energy, even if for the uranium, if I consider Z is equal to 92, that potential energy would be roughly 125 MeV. So therefore, if the electron has kinetic energy 200 MeV, it has to spend 125 MeV to come out of the nucleus. Then in that case, it should have 75 MeV. But no such beta decay with such large energy exists. So therefore, it turns out that electrons do not exist inside the nucleus. Well, do protons exist inside the nucleus? Do neutrons exist inside the nucleus? The momentum basically is the same as the electrons, since uncertainty is the same as the radius of the nucleus. But the mass, however, is 2,000 times larger than that of mass of the electron. So therefore, we use non-relativistic treatment, and then the kinetic energy of the proton and the neutron that is necessary for the proton to stay inside the nucleus or neutron to stay inside the nucleus is of the order of 20 MeV. And then one knows very well that the potential well, that is Woods action potential well, that is used for the nuclear physics is much deeper than 20 MeV. So neutrons and protons can remain inside the nucleus. So that is one important thing, that the first application, as the neutrons can exist inside the nucleus, protons can exist inside the nucleus, but electrons do not exist inside the nucleus. Then another important thing that is basically explained qualitatively by the uncertainty principle is stability of matter and the origin of repulsive interaction. Now, there are two requirements for stability. One requirement is that it must have an attraction at long range and it must have a repulsion at short range. Both things are necessary for stability to occur. So for hydrogen atom, there is attraction due to Coulomb interaction, which corresponds to 1 over r force, potential energy as 1 over r, while the kinetic energy, which corresponds to h upon delta p, because h upon delta x, h upon r. So the kinetic energy is of the order of 1 over r square. So therefore, if the electron is attracted towards the nucleus, as it comes nearer, its potential energy falls, but its kinetic energy increases as 1 over r square. And therefore, it cannot increase that tremendously, and therefore electron cannot fall inside the nucleus. And that is basically what comes because of the uncertainty principle. So the repulsion is because of the electron coming closer to the nucleus, and that repulsion is due to uncertainty principle. Same thing can be explained for the ionic bond of sodium chloride. Sodium chloride, as we know, standard basically says that sodium is positively, the sodium gives out an electron and chlorine accepts an electron. Then sodium ion, chlorine ion, both are spherically symmetric. Since both are spherically symmetric, they will attract because of the Coulomb interaction. But of course, they never fall into each other, because whenever they come closer to each other, electron orbits start coming closer and closer, and electron distribution becomes denser and denser. That basically means uncertainty in the position of the electrons goes on reducing, which means that the uncertainty in the momentum goes on increasing, which means the kinetic energy goes on increasing and total energy goes on increasing. And therefore, reduction in position in uncertainty increase momentum. So that requires increase in energy, and therefore we realize that there is a repulsive interaction. So without that repulsive interaction, we cannot exist, because without repulsive interaction, nothing can be stable. Now, we know that Professor Bohr in 1913 gave the picture of hydrogen atom as an orbit. Now, the way Professor Bohr derived that particular relation is quite unique. Of course, that is not I'm going to talk about. So that is another aspect, that Professor Bohr actually derived that particular relationship not by quantizing angular momentum. He derived in a different way. And quantization of angular momentum is a result of that particular derivation. Anyway, we assume that quantization rule is given as momentum multiplied by r is n times h bar. Now, however we want to talk about the orbit of a particle, orbit of an electron, then in that particular case, we have to talk about, whenever we talk about an orbit, the delta r, that uncertainty in the position or the uncertainty in the radius must be much smaller than r. Then only we can talk about an orbit. We can talk about, and similarly, in order to talk about the velocity of that particular thing, delta p must be much smaller than p. So therefore, if I consider both things together, delta r by r and delta p by p must be much smaller than 1 if I want to talk about an orbit of an electron. Now, uncertainty relationship says that delta r, delta p must be greater than or equal to h bar, approximately h bar by 2. But let us consider h bar. In quantum mechanics, as far as the uncertainty principle is concerned, h and h bar and h bar by 2 are more or less similar. So therefore, delta r, delta p divided by rp, which basically must be much smaller than 1. But delta r, delta p is greater than h upon r upon p, and r into p corresponds to n h bar. So therefore, this particular quantity must be is equal to 1 over n. Now, if a, that is this relationship, and this relationship has to be valid, then in that particular case, n must be much, much larger than 1. That means we cannot talk about the ground state orbit or the first orbit or the second orbit or the third orbit. In order to talk about an orbit, then in that n must be very large. Now this relationship, so therefore this is concept we saw as far as the ordinary n is equal to 1, n is equal to 2 is concerned, we cannot really see an orbit as such. But anyway, this is famous celebrated correspondence principle by Bohr, that whenever the quantum numbers are very large, then the electron or that particular system follows the classical rule, and that is correspondence principle, and that was used by Bohr in order to obtain the his model. The Bohr's model is merely a way to obtain correct energy spectrum of the hydrogen atom. Anyway, now let us come to a peculiar situation that occurs. All right, that because this is a benzene molecule. Benzene molecule corresponds to C6H6. Now, normally that can be written down as 3 double bonds and 3 single bonds. Now, it is known that Kekulé is the person who actually gave that particular structure of gave the structure of the benzene. And there is a story about that particular thing, that he dreamed about that particular thing, that he was very worried about what kind of bonds that are there in benzene molecule. So therefore he slept in his chair, and he dreamt that a snake is eating its own tail, and that from that he realized that the benzene molecule is a cyclic molecule like that, which is a double bond. And so therefore there are two structures, structure 1 and structure 2. The double bonds so therefore there is no distinction between carbon-carbon bonds in benzene. So the double bonds and single bonds must exchange each other. Now chemists are very clever people, and they have actually realized that the single bond length is of the order of 1.54 angstrom, and the double bond length is of the order of 1.34 angstrom. This is studied from various molecules that are there and studied by chemists, and they actually come up with this particular data. But if you look at the benzene as such, the bond length in benzene is neither 1.54 nor 1.34, it is 1.40 angstrom. So therefore it's between single bond and the double bond. So therefore it basically means the double bond and single bond are vibrating, or they are exchanging with each other. And that basically corresponds to that the double bond basically corresponds to pi electrons, and these pi electrons are going from one place to another place. So the electron localization is not there, it's delocalized. So delocalized means uncertainty in position of the electron is larger, which basically reduces the uncertainty in momentum, and that reduces the kinetic energy. Actual work, if you realize that as a consequence of electron delocalization, there is extra binding energy. This is called resonance energy, and that resonance energy is 37 kilocalorie per mole, which when we convert to actual 1 per molecule, it is 1.6 electron volt per molecule. Now 1.6 electron volt per molecule is quite a large number, because whenever we burn anything, the carbon is burnt. One carbon is burnt to carbon dioxide. Roughly the energy released is of the order of 5 electron volts, 5 to 6 electron volt. So therefore, whenever benzene molecule, extra energy is 1.6 electron volt per molecule. And similarly, whenever we talk about naphthalene molecule, naphthalene is a double ring. So here is a single ring. Naphthalene molecule is a double ring. Double ring molecule basically says that it has roughly the 75 kilocalorie per mole, which is roughly double the binding energy here. So now let us go ahead. So this is another place where that resonance structure or uncertainty principle plays a very important role. It plays a very important role in formation of proteins. Proteins are formed by the bond called peptide bond. The peptide bond corresponds to COONH. That is what the peptide bond corresponds to. Now, actually peptide bond, now here the double bond between oxygen and carbon gets shifted to single bond, and that basically electron, the double bond and single bond goes on fluctuating. So that is called basically resonance. So this peptide bond basically gives extra binding energy, because the delocalization of electron, it produces less amount of uncertainty in momentum, meaning less in a kinetic energy, and that energy is roughly order of 23 kilocalorie per mole. That is 1 electron volt approximately. So therefore, the peptide bond is much stronger than a single bond and or a double bond, simply because it has extra resonance energy, and this extra resonance energy gives strength to protein molecule. Not only that, if this was the structure of the peptide bond, then the peptide bond would rotate around that particular single bond. The molecule would rotate, one amino acid will rotate against another amino acid. But since that has a partially double bond character, the amino acids do not rotate with each other, and that gives the structure to the protein molecule. So therefore, that has important effect on the shapes of protein molecules. And that is basically data which says that carbon's N double bond length is 1.48, carbon nitrogen double bond is 1.28, while actual length is 1.32. So it basically forms a resonance between, so electron goes from one place to another place, delocalizes, which increases the binding energy. This is another example which I taken from the book of Feynman, which says the positively charged hydrogen molecule ion. An electron is, whenever we talked about hydrogen molecule ion, that means two hydrogen atoms, one electron has gone out. So therefore, there is only one electron between two protons. So if there are only one electron between two protons, the electron can be associated with one proton, or electron can be associated with another proton. So if they are too far away, then one is hydrogen atom, another is a proton. So therefore, these are, as far as the quantum mechanics is concerned, these are two basis states. One basis state corresponds to electron near one proton, and second basis state corresponds to electron within near the second proton. But as we know, in quantum mechanics, the superposition of states are very important. That if the two states are possible, a superposed state is also possible. So therefore, you can immediately see that as far as the basis state is concerned, you can always make a state called number 1, and that corresponds to 1 minus 2, and 2 which corresponds to 1 plus 2. So these are the two states that are there, which are obtained by the superposition. And it turns out that if I have a state capital I, capital 1, that is state number 1, and state number 2, now you realize that state number 2 has this has plus sign in between. Plus sign in between basically means electron can be found at the center of that particular thing. So electron then in that particular case is delocalized more, while in this case the localization is more, and therefore state number 1 and state number 2 must have larger binding energy. That means it must be lower in energy. And that is so compared to state 2, state 1 has more spread out electron wave function, and delta x is larger, delta px is lower, hence lower in energy. So that basically means uncertainty principle qualitatively explains why state 1 is lower in energy compared to state 2. That is because the electron is inside at the center of the nucleus, center of the two protons. The probability of finding electron there is there. In principle, of course, one can solve the entire thing. You can write down two-state matrix. Electron jumps from one proton to another proton. Detailed analysis one can see in the book of Feynman. This is basically what is the graph that basically corresponds to. State 1 has this kind of energy as it goes up, while state 2 has a minimum, and therefore that is a bound state. So therefore hydrogen molecular ion is bound simply because of the uncertainty principle. Same thing can be talked about for the hydrogen molecule. Now I'm not going to talk about this particular part, simply because if one wants to study this is given very nicely in Feynman's lectures in physics volume 3. Now let us come to the another phenomena which comes because of the uncertainty principle, and that is the natural line width. Natural line width basically comes because of the uncertainty principle. Delta E delta T greater than h bar by 2 relates the lifetime of an excited state with the uncertainty of its energy. Whenever a electron, let us consider an example of hydrogen atom. Whenever hydrogen atom is in excited state, so electron is in higher state, and then it comes to lower state, it makes a transition. So whenever it makes a transition, the transition time basically is controlled by quantum mechanics, right? So quantum mechanics is probabilistic. So therefore, the time for a transition is not fixed. So there is uncertainty in time. That uncertainty in time basically produces that that particular energy is also uncertain. So the photon that comes out because of the transition from one state to another state has an uncertainty in energy, and that uncertainty in energy basically gives rise to whatever is the band, the width of a natural of a line. If you look at any line in a spectroscope, the line in spectroscope is never a single line. It is a Lorentzian profile, and that Lorentzian profile is produced because of the uncertainty principle. That time for transition is not certain, time for transition is not known, there is uncertainty in time. This is basically that gives the line width of any line. This is, if we consider now, let us give an example. Let us take laser coherence time. Laser coherence time for ordinary gas laser is 10 to the power minus 3 seconds approximately. If I consider solid state laser, then it has a time limitation or coherence time of the order of 10 to the power minus 6 seconds. That means for 10 to the power minus 6 seconds, the light beam is entirely coherent. All right. And for ordinary light source, the tau, that time, is of the order of 10 to the power minus 12 seconds. So if I consider delta E corresponds to h upon h, delta E is h upon h into delta nu corresponds to h upon delta T. If I do the calculation, then it turns out that lower limit for solid state laser, if I consider 10 to the power minus 6 seconds, then the delta nu, that is the frequency uncertainty, is of the order of 2 into 10 to the power 5 hertz, while the ordinary light frequency is 6 into 10 to the power 17 hertz. All right, that is the ordinary frequency. So therefore, you can immediately see delta nu by nu is of the order of 10 to the power minus 12, which is very sharp monochromaticity. So therefore, whenever you say it's monochromatic, it is basically because delta nu by nu is coherence time is extremely large, 10 to the power minus 6, while for ordinary light, the coherence time is 10 to the power minus 12 seconds. Now, another important application, theoretical, I mean, understanding of certain part of physics is basically that whenever we consider helium is not liquefied, right? Helium cannot be liquefied. So no liquefaction of helium, right? Helium basically, whenever helium comes out, so therefore you immediately realize helium as a nucleus, helium has only interaction which corresponds to van der Waals interaction. So whenever helium atoms are separated, right, there's, so actually I should not say liquefaction of, actually no solidification of helium. It is not liquefaction, it is solidification of helium. So helium cannot be solidified. Potential energy is given as this, but this is basically potential energy given for the case of helium, that is from because of the van der Waals interaction, and this was calculated in 931. So VR has that particular part. So therefore, energy can be converted to temperature, and the K times T corresponds to energy. So therefore, the minimum of the potential energy of the order of 9K. 9, we cannot say 9 degrees, but 9 Kelvin, right? So for well-defined location in solid, so here the idea is not no liquefaction, it is no solidification. That is a mistake that is there in that particular writing. So this helium cannot be solidified, because if I want to make a solid, then in that case the position of helium atom should be of the delta X should be smaller than the distance between the two, or the lattice distance between the two parts, and that is of roughly of the order of half an angstrom. So if delta X is of the order of half an angstrom, the uncertainty in energy corresponds to the H or uncertainty in energy is h upon delta t, and h upon delta x is the uncertainty in momentum. And if I use that, the energy delta E corresponds to roughly of the order of 10K. So therefore, one realizes that the binding energy maximum can be 9K, while the uncertainty in the energy is 10K. So that basically means helium atom can never stay here in that particular potential well. It will always be above that particular part. So therefore, it is realized that the helium can never be solidified simply because of uncertainty principle. Now, the people actually ask the same question, that how can hydrogen be solidified? Hydrogen has a smaller mass. Hydrogen H2 molecule has a smaller mass than the helium, and therefore delta P, H upon delta P. So delta P. So if I consider that particular part, hydrogen also should not solidify, but hydrogen solidifies under large pressure. A hydrogen solidifies simply because hydrogen does not only have the van der Waals force, it also has force because of the interaction between the two hydrogen atoms, and that is basically, even though helium does not solidify, hydrogen does solidify. Other noble elements do form solids because mass is much larger than that, and that is why helium does not solidify. Other noble gases solidify. Hydrogen also solidifies. Now, this is another example where one can estimate the lowest energy possible for this. This is given mostly in many textbooks, that basically says, let us estimate the ground state energy of the hydrogen atom. The ground state of the energy of the hydrogen atom corresponds to E square, potential energy E square upon R0, where R0 is the extent of spherically symmetric system. So the kinetic energy is of the order of delta P square by 2m, is h square upon 2m r square. So the total energy is kinetic energy plus the potential energy, and that energy is total energy of the system. So if I want to find out the minimum energy of that, I differentiate dE upon with respect to R0, and that produces me R0, which corresponds to h square upon me square, which is basically Bohr radius. And the energy, if I substitute that in the energy expression, then in that particular thing, it gives me m e raised to 4 divided by 2 h bar square. So that basically tells me this is the actual exact energy of the hydrogen atom. It turns out that exact energy relation is an accidental perfect agreement. It is not that uncertainty principle gives you exact ground state energy of hydrogen atom. The accuracy, so it is basically accidental perfect agreement. It is not that uncertainty principle always gives that kind of an agreement. Similarly, for harmonic oscillator x0 is, as far as the harmonic oscillator is concerned, ordinary harmonic oscillator would say that the position of the oscillator or the particle should go at x is equal to 0. But if x goes to 0, its uncertainty in position is 0. Now uncertainty in position cannot be 0, because if uncertainty in position is 0, uncertainty in momentum is infinity, and therefore it would have infinite kinetic energy. So therefore, one must realize that whenever we talk about harmonic oscillator in quantum mechanics, the x0 is roughly the estimated uncertainty bits position. So the particle is not at x is equal to 0, but it goes on vibrating around x is equal to 0. It goes on fluctuating around x is equal to 0. And if that is x0, then the total energy corresponds to kinetic energy plus the potential energy, which corresponds to half m omega square x0 square. And if I minimize that with respect to x0, the ground state energy turns out to be h omega by 2. So this is also another example how uncertainty principle explains certain things about ordinary things, that ground state energy of hydrogen atom and ground state energy of harmonic oscillator. Now let us come to another application of harmonic uncertainty principle in statistical mechanics. We talked about statistical mechanics. There is probability that comes into picture. Statistical mechanics, one talks about the entropy of the system. Entropy of the system, as given by Boltzmann, is k logarithm of number of states, and the number of states corresponds to the phase space volume. Now, as far as the classical statistical mechanics concerned, that phase space volume as basic can be utilized, and there is no need to have any unit cell for the phase space. But in quantum mechanics, that quantum statistical mechanics, Planck's constant h comes in, and that is the value of h. That so the phase space, elementary phase space volume, comes because of uncertainty principle, is h cube if I have one particle, and h raised to 3n if there are n number of particles. Now, this is another important thing that comes into picture. Now, this recently I wrote a small article based on this particular thing. That is vacuum polarization and its role in spontaneous emission of radiation. Now, emission of radiation is become important because of the laser. Laser, whenever we talk about laser, there are two kinds of emissions that are there. One is spontaneous emission and another is stimulated emission. Now, stimulated emission, as we know, is occurring because there is already present the number of photons of that particular frequency. And Planck's law basically gives the black body radiation law, which was discussed yesterday, is given by that particular expression. And Einstein, by the way, this was given by Planck, and this was the Planck. And Einstein later on, in around 1916, talked about this particular theory, which called Einstein coefficients are involved. So whenever two states go from one state to another state, there are two possibilities, R and M. N and M are the two states where N and M, one of them is lower energy state, another is higher energy state. Now, naturally, M is stimulated emission is proportional to number of systems in the excited state. M is the excited state. So the stimulated emission corresponds to basically Bmn and I omega. That basically corresponds to the stimulated emission. And then Einstein wrote down spontaneous emission rate as AMM NM. Now, this is the emission absorption rate naturally will depend upon how many number of photons are present. And that is what is the absorption rate is concerned. In thermodynamics, the Rmn and Rnm at thermodynamics, whenever equilibrium is reached, these two are going to be equal, and that basically gives that particular relationship. And Nm upon Nn corresponds to e to the power h omega by kt, that is Boltzmann distribution. And that is whenever Einstein used that particular relation, he obtained this relationship that I omega corresponds to AMN. And then when he compared that with the Planck's radiation law, he realized that A by B, BMM and BMN must be equal, and A by B must be equal to, and these are basically, this is where Einstein stopped. That is how far Einstein could go. Now, if you realize that as far as the ordinary light coming from the sun is concerned, then in that case, the sun has a temperature roughly of the order of 6,000 Kelvin, and lambda corresponds to 4,000. Let us consider lambda as 4,000 angstrom. Then, as far as the light coming out, the ratio of spontaneous to stimulated emission is roughly of the order of 400. That means spontaneous emission is dominating. Similarly, lambda for 7,000, the ratio corresponds to 30. So there also spontaneous emission is dominating. So the domination of spontaneous emission is simply because of that particular large temperature. Now, as far as the laser radiation is concerned, we want domination of the stimulated emission, and that is basically what corresponds to. Now, if you consider that the emission rate contains that particular thing, if we consider the entire theory, that Rnm corresponds to D. Now, n omega is the number of photons that are present. Now, this basically is the rate that comes out because of the stimulated emission. But this one that is there, that is basically spontaneous emission. That spontaneous emission, one can consider that the emission of spontaneous radiation occurs because of uncertainty principle. Because of uncertainty principle, the photons, there are energy of half h bar omega that is present inside the harmonic oscillator or the mode of that particular vibration. And that half h omega basically produces vibration of that particular thing. So what is called 0-point fluctuation. And this 0-point fluctuation gives that particular thing. And 0-point fluctuation gives that particular factor of 1, and that basically means that the spontaneous emission is also not nearly necessarily spontaneous. It is because it is stimulated by the random fluctuations that are there inside that particular system. So random fluctuation is occurring because of the uncertainty principle. So it is the uncertainty principle basically talks about, gives us why there is stimulated spontaneous emission of radiation. Now one can also talk about that, whether now there are other spontaneous phenomena in nature. Other spontaneous phenomena in nature are radioactivity. That is alpha radioactivity, of course one understands, because alpha particle is produced inside the nucleus, or is the 4 particles come together inside the nucleus, they are vibrating and they basically collide with the wall, and there is tunneling of that particular thing. That tunneling produces alpha radioactivity. But beta radioactivity, we talked about earlier that electrons don't exist inside the nucleus. So beta radioactivity means electrons are produced inside the nucleus. When the electrons are produced, these are also produced because of the quantum fluctuation of that particular field. So anyway, let us go ahead. And so here I talk about tunneling, barrier penetration. Barrier penetration is very important topic in our quantum physics, which this is from a book by I guess I forgot to mention the name of the book that is used. So therefore this is basically whenever we consider that a particular system at energy E, then it will stop at that particular position. But there is uncertainty in delta x. So that delta x has a particular value. Similarly, delta x around that particular thing is this value. If these two delta x overlap with each other, then in that particular case, there is going to be penetration. So therefore, that penetration basically occurs because of uncertainty principle. Similarly, if you consider that penetration in terms of delta E, delta T, there is no fixed energy. So the energy goes up and down, and therefore the particle can come out of that particular thing. So this is another way of understanding why barrier penetration takes place. All right, of course, that. So if the wave function happens to be of the smallest uncertainty product, what is the smallest uncertainty product? Smallest uncertainty product is the product which basically produced by a Gaussian. And ground state of simple harmonic oscillator has a wave function that is merely just for the comment's sake, that Gaussian wave function is the ground state wave function of harmonic oscillator. Now, another important thing that occurs is the range of nuclear interaction. This is what Yukawa used in order to predict the force, that Yukawa force that is there inside the nucleus. The nucleus basically has size of R0, and therefore H upon R0 roughly of the order of MC. Now it is idea that all interactions are because of exchange of something. Electromagnetic interaction is because of the exchange of photons. Similarly, it is considered that the gravitational interaction is because of the exchange of gravitons. Similarly, one can consider that as far as the nuclear interaction is concerned, nuclear interaction is because of some kind of a particle that Yukawa basically assumed, and Yukawa predicted that the mass of that particle should be of the order of 2 upon 50 mass of electron. That is because if we consider delta P as H upon R0, then the mass that produces MC, which corresponds to for relativistic particle, and mass turns out to be of the order of this particular thing, which is roughly 250 mass of electron. And then we realize that pi meson roughly has the same kind of mass. So therefore, Yukawa basically predicted the nuclear range of nuclear interaction. He said that if the pi mesons are exchanged between the protons and neutrons, and protons and protons and neutrons, then in that particular case, the range of nuclear interaction roughly of the size of the nucleus. Similarly, if we consider beta decay, as far as the beta decay is concerned, beta decay or weak interaction is because of exchange. Now, beta decay is considered to be a small, very short range interaction. In fact, Fermi's theory of beta decay says that the nuclear beta decay interaction is zero range interaction. Zero range, of course, there is nothing like zero range interaction. So it must be very small range. So if the range is very small, the mass of that corresponding particle must be very large. And we know very well that as far as the weak interaction is concerned, two bosons are there, W bosons and Z bosons. They have roughly large mass, which corresponds to roughly 81 GeV and 93 GeV. So that basically is because of the new beta decay has a very short range. Now, this is another thing that one is, of course, one cannot really talk about that too much. It is basically whenever we consider superconductivity. In superconductivity, there is a there is a coherence length in superconductivity. Now, as far as the Fermi energy is concerned, Fermi energy is EF, and that corresponds to m upon 2 Vf square. So therefore, delta E corresponds to Vf upon delta P. And if we consider that the band gap or the gap between whenever the Cooper pair is formed, the gap corresponds to roughly of the K times transition temperature. And if we consider that particular thing, then you realize that delta X, that is the Cooper pair, can extend to how long Cooper pair can extend, and that can be obtained, and that basically corresponds to this. So the Cooper length, if I substitute all the values for a relevant superconductor, then in that case, the coherence length roughly of the order of 10 to the power minus 4 centimeter. That is roughly the penetration depth of the superconductivity. The superconducting current flows through the surface of the superconductor, roughly thickness of that particular order. Now here I come to a peculiar situation, that is why that uncertainty principle does not seem to apply for large system. I consider dust particle of 1 micron size, and then if I consider the mass of 10 to the power 1 micron size, you can calculate what is the mass, because the density of dust particle is roughly the density of silicon dioxide, 2.8. You can calculate the mass roughly of 10 to the power minus 15 kg. If the dust particle is in air, it vibrates. It is basically moving approximately 1 millimeter per second. And if you consider that particular thing, then in that particular case, you consider delta P by delta P. The wavelength of that particular particle is 10 to the power minus 6 angstrom, which is much, much smaller. So therefore, we consider that as classical particle, because wavelength, the de Broglie wavelength is very small. Now, as a novel exercise, I did that calculation for coronavirus diameter. Coronavirus particle. Coronavirus, basically, roughly, if you study that, it has roughly the size of 120 nanometer diameter. Now, coronavirus, of course, has two parts. One part is the protein structure that is outside, and inside there is an RNA that is there. So the mass of coronavirus can be calculated, assuming that the density of coronavirus, density of all living matter, is roughly 1 gram per cubic centimeter. That is density of our density of water. And if I consider that, then in that particular case, the mass of that coronavirus particle comes out to be 10 to the power minus 15 gram. There have been several statements that basically, but of course, the RNA mass, of course, is 10 to the power minus 18 gram, but that is inside that particular virus. Now, assuming mean kinetic energy of roughly of the order of kT, right? If kT is roughly the velocity comes out to be coronavirus particle, if it is there in the air, it is 9 centimeters per second. And then corresponding de Broglie wavelength, if I calculate, the de Broglie wavelength corresponds to 0.00007 angstrom, which is much smaller than 129 nanometers. So therefore, coronavirus also obeys classical laws as far as the transmission from one place to another place is concerned. And that, of course, these days we know coronavirus has revolutionized our way of living. And anyway, that is besides the point. There is a role in philosophy. Quantum mechanics or uncertainty principle has a role in philosophy. Laplace wrote a book as far as celestial mechanics and is presented to Napoleon. Napoleon glanced through that particular book and asked him, why there is no mention of God in that particular book? Laplace then replied that he did not feel it necessary to include God in that particular thing, because God is not necessary. So anyway, that is basically the idea. Laplacian dream is basically that you can do calculation, everything is deterministic. All laws of physics are deterministic in origin. So therefore, entire thing can be deterministic. But of course, statistical mechanics, because we cannot do that particular thing. But that is the Laplacian dream. Laplacian dream basically says everything in the world is deterministic. But as soon as the uncertainty principle enters, uncertainty principle basically says that nothing is certain. Everything is uncertain. Everything in the life is uncertain. Everything is uncertain. Not only that, Einstein added principle of locality. as far as, because Einstein gave the general theory of relativity, and he talked about that particular thing, and that unlocality is also gone because of quantum mechanics. All right. There are many aspects to be discussed as far as the philosophy is concerned, the consciousness, and so on and so forth. But so far, we don't have that much amount of time to talk about that particular thing. In classical physics, there is unity. In quantum mechanics, that is replaced by duality. And Bohr was the first to identify this feature. He termed it complementarity. So that is basically what. Now, resonance particles in particle physics have lifetime related to width of the particle in the experiment. Another small notational thing that one has to understand, that as far as the molecular energy information transfer is concerned in our body, information is transferred from one, for a DNA molecule stores the information, and it is transferred by DNA to RNA, and RNA goes to mitochondria in order to form, in order to construct proteins. So in order to construct protein, information has to get transferred from DNA to RNA and RNA to mitochondria. Now that information transfer must be done by a large molecule, because if the information is transferred by a small molecule, quantum fluctuation would produce large number of fluctuations, and that would basically increase the number of mutations, and that would increase the, good or bad, I don't know. But anyway, as far as the life is concerned, the information transferred is always by very large molecule. Now, this is something which Professor Joshi would have talked about, that is Hawking radiation. Hawking radiation is also because of the uncertainty principle, that around singularity, you can produce, because of quantum fluctuation, electron-hole pairs. One particle goes inside, other particle goes away, and that basically produces radiation somewhere else, and that is basically Hawking radiation. And that is more or less all that I wanted to talk about. I thank you very much for listening to me.
Sir, there are some questions, and you can see them in your Q&A tab. You can choose some questions to answer, sir. Or shall I do it for you?
Well, you can give an insight on entropy information theory of explaining black hole. Now, I do. The first question that is there in explaining black hole, Professor Joshi would have talked about that particular thing. Does parallel universes really exist? Now, these are the theories. Whether they exist or not, it is a viewpoint that one particular person takes. Whether that really exists or do not exist, that is another viewpoint of the quantum mechanics. I don't know. Many things that are there are not my. That is not.
Sir, I think. Okay, sir. Sir, I actually dismissed all other questions, but I'll read these questions for you now, which have come in your talk. Okay. What is the physical interpretation about Schwarz inequality? Does it have any relation with uncertainty?
Schwarz inequality and uncertainty principle. No, actually, that is not related. Schwarz inequality is related to something else. That is not related to this particular thing.
Okay. Now another question which is asked is, are there any other conjugate quantities other than position, momentum, energy, time, and J theta?
Well, these are the only three things that are there as far as the conjugate parameters are concerned. If we consider many dimensional, as in quantum cosmology, one talks about, or particle physics, one talks about many dimensions, that as far as the strings are concerned, the strings are dimensionality is much more than 10 or something. Then in that case, there will be many more conjugate variables in that particular theory. But as far as ordinary things are concerned, we talked only about the position, momentum, time, energy, and angle and angular momentum.
Okay. Sir, another question. There are two similar questions. I'll read out one of them. In double slit experiment, the understanding that a single electron is present at both the slits as a result of probability, and it is just a statement. That's what he's writing. How can this statement or understanding explain the interference pattern by a single electron?
Well, interference, as far as the single electron is concerned, single electron, whenever it falls on the screen, gives you one particular spot. And that particular spot does not tell you whether there is an interference or not. But that spot normally occurs whenever the interference pattern maximum would occur. And if the number of electrons or number of photons keep on increasing, they will fall more or less at the place where the slit, more or less where the maximum of the intensity should occur. And then as the number of photons and number of electrons goes on increasing, as Tonomura's experiment actually shown, that slowly and slowly the interference patterns will develop. So as far as one individual electron is concerned, whether that gives rise to uncertainty or the interference pattern is, of course, one electron cannot show you interference pattern. In order to see interference pattern, you must have many electrons or many photons. And that is the reason why a single, but of course, you realize that the interference pattern is produced, definitely produced. And that means that an individual, according to as the Dirac basically says, an electron interferes with itself. And otherwise, you cannot never obtain interference pattern with many electrons also. So therefore, it is basically a situation that single electron also produces interference pattern.
Okay. Okay. Sir, another question is by Monojit Chatterjee. He says that if hydrogen is in first excited state, then it can only release an exact amount of energy. The difference between the energy of n equal to 2 and n equal to 1 state is exactly same every time. Where is the uncertainty in energy in all these things?
Well, it is not, as far as the energy is concerned, whenever the energy is given out, so transition time is basically involved. Transition time is involved. So therefore, the transition time is uncertain. And therefore, there is uncertainty. So that is the reason. Now, the photons that come out from various hydrogen atoms, if you take the spectroscopic photograph, then you realize that all photons do not have the exactly same wavelength. They may have different wavelengths. And that is why there is a line width. The line width is not an experimental error. It is actually really present there. And that line width basically means the energy of the n is equal to 2 state and energy equal to 1 state are not exactly known. So therefore, whenever the energy transfer takes place or the transition takes place, the energy that is given out to the photon is not exact, it is uncertain. Okay.
Hello.
Sir, there is another question. Is time travel possible with the help of quantum mechanics in future?
Time travel is possible or not? Time travel. Now that is another question that Professor Joshi would basically answer very nicely. Whether time travel is possible or not. There are many novels, many science fictions that are written for the time travel, and that of course there are fallacies that are present there. That if I go back and kill somebody and then later on come back here, whether that is possible or not. These are fallacies that are there in time travel. Whether time travel is possible or not, that is clear. Of course, that is basically, as far as the time cone is concerned, in curvilinear geometry, time cone can have different directions, and therefore time travel is possible in that particular case.
Okay, sir. I think we will take a last question, which is again probably between both the talks. Does wormholes have anything to do with uncertainty?
I don't know. I don't know about that particular part.
Okay, fine. So I think we can close for today.
Yes.
Whatever other questions we have, we will be sending it to you, sir, later.
Okay.
Yeah. Thank you, sir.